Welcome to a deep dive into one of the most fundamental and precise techniques in all of analytical chemistry, acid-base titration. Before we get into the nuts and bolts, let's establish a foundation. What exactly is titration? The definition is that it's a quantitative technique, meaning it gives us exact numbers, used to determine the concentration of an unknown substance. Its underlying principle is simple, the neutralization reaction, where an acid and a base react perfectly to form salt and water. The detection of this perfect reaction is shown by a visual cue, usually an indicator which signals the equivalence point. Well, titration, as we know it, didn't appear overnight. Let's meet the pioneers. First up, Francis Antoine Henry, often called the father of titrimetric analysis. He gave us the volumetric analysis and developed the first form of the burette way back in 1791. That's actually revolutionary. Now, stepping into the 19th century, we have Carl Friedrich Moore. Moore is the reason our modern lab work looks the way it does. He redesigned the burette, simplifying and improving it, and wrote the very first comprehensive analytical chemistry textbook that showcased the technique. He truly modernized the field. And to complete this theoretical framework, we credit Svante Arrhenius. His pivotal contribution, the Arrhenius acid-base theory in the 1880s, defined acids as H plus and OH minus. This theory provides the core chemical understanding for the neutralization principle used in titration. Now, let's get our terminology straight. The titrant is the solution whose concentration, it's the one you drip from the burette. The analyte is the solution whose concentration you're trying to determine. It's the unknown concentration. It's sitting down there in the flask. And next, for next key terms, this is where precision matters, the equivalence point. The equivalence point is the theoretical point where the acid and base have reacted completely and are chemically neutral. The endpoint is the visual point where the indicator changes color, signaling that the equivalence point is ideally reached. Now, speaking of indicators, the indicator is a dye that changes color based on the potential of hydrogen. Our goal in any good titration is to choose an indicator so that the visible endpoint occurs at nearly the exact same moment as the chemical equivalence point. Ideally, as I said, they occur at the same time. This brings us to the crucial role of the indicator. You don't just grab one off the shelf. Actually, indicators are specifically chosen based on the pH at which the reaction reaches equivalence. Remember, different acid-base combinations neutralize at different pH values. Now, actually, for the common indicators, we have a few common go-to indicators. First is phenolphthalein is a favorite, turning from colorless in acid to a brilliant pink in base, usually around pH of 8.2 to 10. And for the acidic range, methyl orange is used, shifting from red to yellow around pH of 3.1 to 4.4. So, let me give you the rule of thumb for choosing the right one. For a strong acid plus a strong base titration, either works. The equivalence point is 7. So either phenolphthalein or methyl orange works, but for a strong acid and a weak base, use methyl orange. For weak acid plus strong base, use phenolphthalein. You must get this wrong and your results will be way off. Well, while we focus on a few examples, know that there are four main types of acid-base titrations. This is a strong acid versus strong base, the weak acid versus strong base, the strong acid versus weak base, and the weak acid versus the weak base. Well, actually, each produces a different characteristic curve, which was shown previously. Now, for the math, all titration calculations rely on the fact that at the equivalence point, the moles of acid equal the moles of base, since moles are molarity multiplied by volume. For a 1-1 reaction, the shorthand equation is M1V1 equals the M2V2. Now, this is the equation we manipulate to find that the unknown concentration or molarity of the analyte. Now, actually, what is shown here, this is a 1-1 reaction. And as you can see here, by rearranging the formula, you can isolate the M unknown on one side to find, well, the analyte. Now, actually, just to remind you of the basic relationship, concentration times volume gives you the number of moles. This simple triangle is the secret behind the whole, well, titration calculation. Well, titration isn't just an exercise, it allows precise quantification, which is the key in pharmaceuticals, food quality, and environmental testing. It converts theoretical stoichiometry, moles, and molarity into measurable real world data. I guess we can say it's accuracy, observation, and analytical thinking. Well, of course, no lab technique is perfect. We have to watch out for sources of error, like parallax when reading the meniscus on the burette, air bubbles which throw off your measured volume, and of course, choosing the wrong indicator or dealing with contained glassware. Now, actually, here, the most elegant visual presentation of this technique is the titration curve. Well, it is the graph that plots the pH of the solution against the volume of titrant added. As you can see here in this visual representation, you can pause actually here to see. Remember, 7 is the equivalence point. Well, to quickly summarize, titration determines an unknown concentration. It's based on neutralization, and the key is achieving equivalence. And, well, by the indicator at the endpoint, the math often simplified to, well, M1V1 equals M2V2. Depends on careful measurement and observation. And, well, mastering titration is mastering chemical quantification. Keep practicing, and you'll be running perfect analysis every time. Well, that's it. Okay. Thank you.